So, dear students, today, as I informed you in the previous session, we are going to take up a new concept, moving coil galvanometer. Okay, it's a device. In short, it is also called as MCG. Okay, moving coil galvanometer. Basically, what's a galvanometer? Galvanometer is a device, electrical device, which is used to show the presence of electrical current. Okay, galvanometer is not normally used to measure the current. We did not use to measure the current, but it's used to show the presence of current. But yes, this the same principle of galvanometer, okay, or the basic mechanism of galvanometer itself is used in both ammeter and voltmeter. Ammeter is the device which is used to measure current through a circuit or current through any branch of the circuit. And voltmeter is a device which is used to measure the potential difference across the terminals of a circuit or a device. And both ammeter and voltmeter works on the basic principle of galvanometer itself. In fact, a galvanometer itself is then converted into voltmeter and ammeter. Okay, so first, if we understand the basic mechanism of galvanometer, we can extend the idea to understand voltmeter and ammeter. So today we are going to take up moving coil galvanometer. As the name itself says, we will have a moving coil which can show the presence of current in the circuit. Basically, we all know that when we have a current carrying coil kept in the external magnetic field, that current carrying coil will experience certain torque, isn't it? We are going to make use of same principle here. Okay. So what we need is the external magnetic field set, right? We have actually discussed uh, we have already discussed the amount of torque experienced by a rectangular coil, isn't it? Tau is equal to m cross b. And we are going to extend the same idea here. Instead of rectangular coil, we will have now a circular coil. But that circular coil is owned onto a soft iron core. Okay, we'll take a cylindrical or spherical core, and we will wound that coil or wires in make them into turns on the spherical or cylindrical soft iron core chosen. So somewhat like this. If I have a soft iron core like this, and I'll have turns of conductor wound on that like this. Okay, like this. Now a pointer is attached to the soft iron core. See, this is soft iron core, and these are the external magnets. Say this is north pole, this is south pole. So the magnetic field lines would be pointed towards the core and would be away towards the south like this. So the magnetic field would be set like this. The reason for using the reason for using soft iron core, okay, is to strengthen the magnetic field. More the magnetic field, better the effect of turning. So we want strong magnetic field. In order to get strong magnetic field, we are introducing this soft iron core. Okay, and this is the source for the external magnetic field. That's it. A simple magnet. Two magnets kept like this, north and south. And now uh, two terminals, two wires from one end, one from this end, the other from the other end, are taken and connected to the source of the current, say directly to the battery. Normally it's not directly connected to the battery, but I am taking for a small current, because galvanometer is very sensitive device. Okay, a small current, very small current is enough to show the deflection. That's why. So assume that certain current flows through the coil. Then what happens? Due to the flow of current in the circular shape, circular path, this coil produces its own magnetic dipole moment, and that magnetic dipole moment in the external magnetic field will experience torque, isn't it? What is the torque experienced? Yeah, torque experienced by that is the basic expression that we have already derived in vector form is tau is equal to m cross b. Okay. So now one thing is clear: if we apply certain torque, the entire core, okay, will rotate because it experiences certain torque. Once it rotates, the pointer moves. When the pointer moves, we can get the reading. But the problem with this kind of approach is the pointer keeps on moving once the torque is applied. See, when you have a when you have some rotating device, or you assume that the same old example of rotating gate. Okay, so if I push one end of the gate, it will keep on rotating if there is no sufficient friction. If you have sufficient friction, the amount of rotation that you give will be directly proportional to the deviation that happens in the uh, gate, the rotating gate. Similarly, we need something which can restrict the pointer from moving always to the final point or the maximum point, maximum reading. That's what happens when we do not have something to pull back. When you assume the rotating gate, there is friction, so it stops. If there is no friction at all, then for any amount of force that you give, it keeps on rotating. Any amount of torque actually, for any amount of torque produced, it will keep on rotating, keep on rotating. In the same way, for any amount of current, it will go to the final point and stand. Okay, if you give more current, it will go faster. If you give less current, it will go slower. But finally, it will go and end up in the final point or the maximum reading. So we want to bring it back and restrict its motion from going into the maximum point. For that purpose, what we are going to do is introduce a spring. Okay, introduce a spring so that this spring produces a reverse torque. When this spring produces a reverse torque, torque from the current or due to the magnetic effect, and the torque due to this spring, when they balance each other, the pointer goes and stands at particular point. So more the torque, more the rotational or the reverse torque produced, and the pointer goes and stand and on the next reading, and that's how it keeps on going to the higher readings. So we need a spring to restrict the motion or to produce the reverse torque so that the pointer is restricted to the proper reading. Clear? So now that spring will act as uh, the act as the object which will help us. This will help us in restricting the pointer to from going to the final reading every time. So this is about the construction of moving coil galvanometer. Two strong magnets to produce the magnetic field, to set the external magnetic field, and a soft iron core. Okay, this part is soft iron core on which we have a conductor wound on it in circular path. When and a pointer is connected to the spring actually, okay, not to the core. So when the current flows through the coils, certain torque is produced due to the magnetic effect, and the spring also produces the reverse magnetic effect. So when they balance each other, a particular reading shall be seen, and when we switch off the current, it will come back to the zero reading again. Okay, so this spring plays an important role. We'll actually see how a galvanometer works in few minutes from now. Just a minute. So, the basic principle on which this moving coil galvanometer works is very simple. A current carrying coil in the presence of external magnetic field experiences a torque, right? That's the basic principle of this. Principle of moving coil galvanometer is a current carrying coil experiences uh, a current carrying coil in the presence of magnetic field. In the presence of external magnetic field, in the presence of external magnetic field experiences a torque, right? So now here comes the derivation part or the mathematical part of the galvanometer. So what is the torque expression? Uh, M is the magnetic dipole moment given by NIA. N is number of turns, I is the current through the turns, A is the area of cross section of the turns. So magnitude of torque produced due to the current flowing through the coil is tau is equal to NIAB. Number of turns, current through each turn, area of the turns, area of the coil together, B is the external magnetic field due to the magnets that we have kept. And now, see, as similar to force, see, whenever I take force, it's always linear, okay, linear motion that we see. And when I say torque, it is circular or rotational motion that we see. Now, when we have a spring like this and apply a certain force, what we see, a property of spring is called spring constant, right? Which is the ability of the spring to stretch or compress upon the application of external force. So now, this is a linear force and the expression that we obtained is F is equal to minus Kx, if you can remember it, for the spring connection between spring force and the elongation, isn't it? F is equal to minus Kx. Neglect the sign, it's about, when we take this magnitudes, F is equal to Kx. X is the elongation, linear elongation, K is the linear spring constant, F is the force. Similarly, here also we have a spring, but the kind of motion happening is not linear, instead it is rotational. So instead of F, I should now take torque tau, which is equal to certain spring constant, which I will take again as K itself. But this time this spring constant is rotational spring constant, but I will keep the symbol as K itself. And instead of X, X is the linear motion that was happening. And instead of X, I will take phi, which is the angular deflection that I am observing due to the current. So instead of X, I will put phi. Okay. So when this much of torque is produced due to the magnetic effect, this much of reverse torque is produced due to the presence of spring. So when they balance each other, the pointer goes to certain point and stays. More the current, more the reverse torque, more the reading that we see. Okay, it will go and stand there. In the absence of spring, yes, it would go like this. Small current, it would go like this. It would never stand at a point. Large current, it would go faster, but we could not get a proper reading. In order to get proper reading, we are using the spring. So this is this torque produced due to the magnetic effect, and the reverse torque produced in the spring is given by tau is equal to k phi, where k is rotational spring constant of the spring. Rotational spring constant of the given spring. So now, taking these two expressions, what we are more bothered more is about the dependence of phi, because phi is the angle through which the deflection is happening. So more the deflection, more the value of phi. So this phi itself is what something which can give us the reading of the current. So now we need to connect the dependence of phi on the current coming into the coil. So equating these two, what we will have is k phi is equal to n I a b, and what phi becomes equal to is n a b by k, n a b by k into I. Why did I keep I outside? Look at these factors inside the bracket. What we see is n is a constant, number of turns. A is the area of the coil, which is also fixed. We will not change the coil. B is the magnetic field set, which is also fixed. K is the spring constant, which is also the constant value for the given spring. So according to for a given galvanometer, these factors N, A, B and K are constants, and hence NAB by K together is a constant for the given galvanometer. So this is how we can see the deflection that we see, angle of deflection that we see is directly proportional to the current through the circuit. And this factor NAB by K, okay, when we take, this is the end of the derivation, phi is equal to NAB by K into phi, K into I. But when I take the factor I to the LHS, it becomes phi by I is equal to NAB by K. And we take this factor NAB by K together as current sensitivity. Okay? Yeah, we'll take and discuss all those things. Before I move forward for current sensitivity and voltage sensitivity, I would like to show the actual moving coil galvanometer, how does it work and all. Okay, let's go and see how it works. So, dear students, now what you are looking at is a galvanometer. Okay, here it is written G, galvanometer, and here you have the current sensitivity mentioned, which is 20 microampere per division. Okay, we'll discuss detailedly about it, nothing to worry, but you keep this much in mind, that this galvanometer, when current flows through the terminals, when I connect the terminals here, the conductors here, when the current flows through this, the current should be very small current, microampere, and when it flows through that, there we can see the deflection happening. So more the current, more the deflection, lesser the current, lesser the deflection. So this is the same galvanometer from which I have removed all the frames and readings, because I wanted to show you the inner mechanism and construction. So if you can observe closely here, what you can see here is, this is the pointer which can deflect, okay, and here you have the coil of current carrying conductor, okay, and the ends of this coil will be going through this wire, okay. So one end is this black colored, which will come to this and go here. The other wire is this red colored, which will go to this terminal, positive, okay. So when the current flows through this, current also flows through these small wires, this coil, which is made up of so many turns, as you can see. And now if this is the soft iron core that I was talking about. Okay, this soft iron core is actually now has a good magnetic strength. Okay, if you can observe it, it's actually attracting the attracting this. Okay, because it is attained magnetic property. Okay, and that itself will give the necessary magnetic field here. Okay, right now what else do we have to observe? Here you can see the spring. Okay, observe carefully, it's a very sensitive spring. I hope you can see it. Not sure how clear is this for you. Okay, just try to observe this. Here is the spring. Okay, here you have the spring. See, in the absence of spring, the pointer would keep on moving like this. But since you have the spring, the pointer would come back to its position and it will stay at one position for particular current flowing through that. Right, let us make certain current flow through the galvanometer and see how the deflection happens. Okay, these are all the connections, no need to worry, we'll get to know. This is the resistance that I have connected because I don't want too much current to flow through the galvanometer and damage it. So external resistance is connected here to avoid too much of current flowing through the galvanometer. Okay, this is negative terminal of the conductor of the source, DC source that we have. Negative terminal is coming here and going to the negative terminal again. Right, now I'll switch this on and you just observe how the deflection happens. Did you see that? So when the current flows through this, certain torque is produced and hence the deflection is produced in the galvanometer, moving coil galvanometer. Okay. Now see, here is the point it stopped. In the absence of the spring, it would keep on going to the next or the maximum reading that is possibly could be produced like this. See, it would end up here, but since we have spring, it would come back to the actual reading and stay there. Okay, so that's the significance of spring, to produce the reverse torque so that the pointer reads the proper reading. So now this is the inner mechanism, construction and working. Now the actual galvanometer looks somewhat like this. See, the same galvanometer. This time what we have here is the points or the readings. Okay, now each of this reading, okay, each of them reads 20 microampere, each reading, each division. So now it has moved by 18 division and you can guess the current, 18 into 20 microampere. So which is going to be 360 microampere of current, very small current, 0.36 milliampere. So basic intention of using galvanometer is not to measure the current, instead to get the to know the presence of current. So now we can get to know, yes, there is current, that's it. To measure the current, we have other instruments, which is ammeter. We'll discuss those things later. Okay, I hope you're clear with the construction and working of the galvanometer. Clear? So now The expression that we finally obtained for the amount of deflection is n phi is equal to n a b by k into I. So now we'll define a term called current sensitivity. Okay. So very simple, how sensitive the galvanometer is. If the galvanometer is too much sensitive, it should deflect more for little current. If the galvanometer is less sensitive, it will not deflect considerably good, even when good current is flowing through that. Okay, that's about sensitivity, the regular psychological term. So current sensitivity is defined as the deflection produced in moving coil galvanometer when 1 ampere or unit current flows through is also fine. Okay, 1 ampere or unit current flows through the coil. Okay, and the current sensitivity mathematically is equal to phi by I. Okay, phi by I is itself is the current sensitivity mathematically, which is equal to n a b by k. See, current sensitivity is a constant for the given galvanometer. As you can see, all these terms are constant, and hence n a b by k together is also a constant. Phi by I, the term shows how sensitive the device is. If for less current, the galvanometer is showing more deflection, then phi will be greater, I will be lesser, and hence the ratio will be a larger value. And hence we can say the device or the given moving coil galvanometer is more current sensitive. If you are getting less deflection for more current, then we can say the ratio mathematically becomes lesser, because numerator will be lesser than the denominator. Not exact numerically, but it's about the comparison of different values. You can just think over it, it's all mathematical. Then the ratio becomes lesser, and hence we say the given galvanometer is less current sensitive. And similar to current sensitivity, we also have voltage sensitivity. Let me define that here itself. Voltage sensitivity of given galvanometer. Look at this, the same kind of one. Deflection produced in moving coil galvanometer when instead of 1 ampere current flowing through the galvanometer, we should now take when 1 volt of potential difference is maintained across the terminals of the MCG. Okay, so it is deflection produced in MCG when 1 volt or unit potential difference is maintained across the terminals. So here current sensitivity is phi by I, and voltage sensitivity must be phi by V. Okay, deflection per unit voltage, phi by V. And now how do we get the expression for this? What is V equal to? Phi by V. V is equal to IR. I is the current through the galvanometer. What is this R? R is the resistance of the galvanometer. See, when we were discussing about Wheatstone's network, there we considered the galvanometer has its own resistance, the internal resistance of the galvanometer. We took that the internal resistance or the resistance of the galvanometer as G, capital G, isn't it? So every electrical device, whether it's measuring one like ammeter, voltmeter and galvanometer or any other device, everything will have its own resistance. So even galvanometer will have its own resistance. So that itself this R. Okay, I is the current through that, which is same as this I, but R is the resistance of the galvanometer, which is also a fixed value. Okay, the resistance of the galvanometer is again a fixed value. See, normally the galvanometers that we have will have the resistance somewhere like 100 ohm, 100 ohm, 120 ohm and all. Okay. So, every galvanometer will have its own resistance, keep that in mind. So, phi by IR is what it becomes. Again, resistance is a constant. What does this resistance depend on? Resistance depend on number of turns of the coil, isn't it? More the number of turns, more the resistance. So now phi by IR, uh, we do know what is phi by I equal to. Phi by I is equal to NAB by K, and hence phi by IR becomes equal to NAB by KR. Okay, that's it. NAB by KR is the voltage sensitivity of the given galvanometer. NAB by KR. The extra term R is the uh, resistance of the galvanometer. So now you can see here, if the question is on what factors does the current sensitivity of the galvanometer depend on, then you can easily answer current sensitivity of the galvanometer is directly proportional to number of turns, directly proportional to area of the coil chosen, directly proportional to the external magnetic field set, and inversely proportional to the spring constant of the given spring. Okay. So, that is about current sensitivity and dependence of current sensitivity on other factors, and even the voltage sensitivity and dependence of voltage sensitivity on other factors. Yeah, I forgot to tell you the units of this. It's quite simple, you can analyze it. Phi is the deflection happening, or angle of deflection happening. Okay, it's angle. So, it's radian, right? So, the SI unit of current sensitivity is radian per ampere, right? Radian per ampere. Here, SI unit of voltage sensitivity is radian per volt, right? This is the SI unit of current sensitivity, and this is the SI unit of voltage sensitivity. And now, yeah, dependence of voltage sensitivity. If in the same way we interpreted the expression of current sensitivity, we can also interpret the expression of voltage sensitivity. Here we have NAB by KR, and yes, it is the voltage sensitivity is dependent on area of the coil, magnetic field, external magnetic field, spring constant, and all, even the internal resistance. But it is not dependent on the number of turns, even though you can see the value of n here. The term n is there here, but the voltage sensitivity is independent of number of turns. The reason being, see, if you increase the number of turns, the resistance of the galvanometer will also increase. Following? So, once we increase the number of turns, the resistance of the coil will also increase by the same amount, and hence the number of turns factor will cancel in both numerator and denominator. Okay? Yeah, even though it is given in the reference, do not consider that point. The voltage sensitivity is not dependent on number of turns. Be clear with that. Because if we increase the number of turns in the coil, the resistance of the galvanometer will also increase by the same amount, and hence they nullify their effect on voltage sensitivity. But they are dependent on A, B, K and R. Okay? Because R is something which is dependent on so many factors again. Because R is dependent on number of turns, that's true obviously, but R is also dependent on other factors like the nature of material chosen for that wounding coil, and the temperature. All those things all those factors work, very well. Area of cross section, length and all. Okay, so nothing to worry about that. So this is how much you should keep in mind. Voltage sensitivity doesn't depend on number of turns, but yes, it does depend on area of the coil, magnetic field and spring constant, and resistance of the coil. Okay, that's about current sensitivity and voltage sensitivity of the given moving coil galvanometer. And in the next session, we are going to discuss how to convert this moving coil galvanometer into ammeter and into voltmeter. Okay, and that finishes the chapter. Thank you.